disk drive, HDD, hard disk, hard drive, or fixed disk. B is an electromechanical data storage device that stores and retrieves digital data using magnetic storage in one or more rigid rapidly rotating platters coated with magnetic material. The platters are paired with magnetic heads, usually arranged on a moving actuator arm, which read and write data to the platter surfaces. Data is accessed in a random access manner, meaning that individual blocks of data can be stored and retrieved in any order. HDDs are a type of non-volatile storage, retaining stored data even when powered off. Modern HDDs are typically in the form of a small rectangular box. Introduced by IBM in 1956, HDDs were the dominant secondary storage device for general-purpose computers beginning in the early 1960s. HDDs maintained this position into the modern era of servers and personal computers, though personal computing devices produced in large volume, like cell phones and tablets, rely on flash memory storage devices. More than 224 companies have produced HDDs historically, though after extensive industry consolidation most units are manufactured by Seagate, Toshiba, and Western Digital. HDDs dominate the volume of storage produced, exabytes per year, for servers. Though production is growing slowly, by exabytes shipped, sales revenues and unit shipments are declining because solid-state drives, SSDs, have higher data transfer rates, higher areal storage density, better reliability, and much lower latency and access times. The revenues for SSDs, most of which use NAND flash memory, slightly exceed those for HDDs. Flash storage products had more than twice the revenue of hard disk drives as of 2017. Though SSDs have 4 to 9 times higher cost per bit, they are replacing HDDs in applications where speed, power consumption, small size, high capacity, and durability are important. Cost per bit for SSDs is falling, and the price premium over HDDs has narrowed. The primary characteristics of an HDD are its capacity and performance. Capacity is specified in unit prefixes corresponding to powers of 1000, a 1 terabyte TB drive has a capacity of 1000 gigabytes, GB, where 1 gigabyte equals 1,109 bytes. Typically, some of an HDD's capacity is unavailable to the user because it is used by the file system and the computer operating system, and possibly inbuilt redundancy for error correction and recovery. Also, there is confusion regarding storage capacity, since capacities are stated in decimal gigabytes, powers of 1000, by HDD manufacturers, whereas the most commonly used operating systems report capacities in powers of 1024, which results in a smaller number than advertised. Performance is specified by the time required to move the heads to a track or cylinder, average access time, adding the time it takes for the desired sector to move under the head, average latency, which is a function of the physical rotational speed in revolutions per minute, and finally the speed at which the data is transmitted, data rate. The two most common form factors for modern HDDs are 3.5-inch, for desktop computers, and 2.5-inch, primarily for laptops. HDDs are connected to systems by standard interface cables such as PATA, parallel ATA, SATA, serial ATA, USB, or SAS, serial attached SCSI, cables. Fourth point, competition from SSDs. HDDs are being superseded by solid-state drives, SSDs, in markets where they're higher speed, up to 4,950 megabytes, 4.95 gigabytes per second for M.2, NGFF, NVMe SSDs, or 2,500 megabytes, 2.5 gigabytes per second for PCIe expansion card drives. Ruggedness and lower power are more important than price, since the bit cost of SSDs is 4 to 9 times higher than HDDs. As of 2016, HDDs are reported to have a failure rate of 2 to 9% per year, while SSDs have fewer failures, 1 to 3% per year. However, SSDs have more uncorrectable data errors than HDDs. SSDs offer larger capacities, up to 100 TB45, than the largest HDD and/ or higher storage densities. 100 TB and 30 TB SSDs are housed in 2.5-inch HDD cases but with the same height as a 3.5-inch HDD, although their cost remains prohibitive. A laboratory demonstration of a 1.33 TB 3D NAND chip with 96 layers, NAND commonly used in solid-state drives, SSDs, had 5.5 Tbit/in2 as of 2019, while the maximum areal density for HDDs is 1.5 Tbit/in2. The areal density of flash memory is doubling every 2 years, similar to Moore's law, 40% per year, and faster than the 10 to 20% per year for HDDs. As of 2018, the maximum capacity was 16 terabytes for an HDD, and 100 terabytes for an SSD. HDDs were used in 70% of the desktop and notebook computers produced in 2016, and SSDs were used in 30%. The usage share of HDDs is declining and could drop below 50% in 2018 to 2019 according to one forecast, because SSDs are replacing smaller capacity, less than 1 terabyte, HDDs in desktop and notebook computers and MP3 players. The market for silicon-based flash memory, NAND, chips, used in SSDs and other applications, is growing faster than for HDDs. Worldwide NAND revenue grew 16% per year from $22 billion to $57 billion during 2011 to 2017, while production grew 45% per year from 19 exabytes to 175 exabytes. Now, as we have understood the basic, now we will cover some important points. First, technology. A modern HDD records data by magnetizing a thin film of ferromagnetic material F on both sides of a disk. Sequential changes in the direction of magnetization represent binary data bits. The data is read from the disk by detecting the transitions in magnetization. User data is encoded using an encoding scheme, such as run-length limited encoding, which determines how the data is represented by the magnetic transitions. A typical HDD design consists of a spindle that holds flat circular disks, called platters, which hold the recorded data. The platters are made from a non-magnetic material, usually aluminum alloy, glass, or ceramic. They are coated with a shallow layer of magnetic material, typically 10 to 20 nanometers in depth, with an outer layer of carbon for protection. For reference, a standard piece of copy paper is 0.07 to 0.18 millimeters, 70,000 to 180,000 nanometers. The platters in contemporary HDDs are spun at speeds varying from 4,200 RPM in energy-efficient portable devices, to 15,000 RPM for high-performance servers. The first HDDs spun at 1,200 RPM and, for many years, 3,600 RPM was the norm. As of November 2019, the platters in most consumer-grade HDDs spin at 5,400 or 7,200 RPM. Information is written to and read from a platter as it rotates past devices called read and write heads that are positioned to operate very close to the magnetic surface, with their flying height often in the range of tens of nanometers. The read and write head is used to detect and modify the magnetization of the material passing immediately under it. In modern drives, there is one head for each magnetic platter surface on the spindle, mounted on a common arm. An actuator arm, or access arm, moves the heads on an arc, roughly radially, across the platters as they spin, allowing each head to access almost the entire surface of the platter as it spins. The arm is moved using a voice coil actuator or in some older designs a stepper motor. Early hard disk drives wrote data at some constant bits per second, resulting in all tracks having the same amount of data per track, but modern drives, since the 1990s, used zone bit recording, increasing the write speed from inner to outer zone and thereby storing more data per track in the outer zones. In modern drives, the small size of the magnetic regions creates the danger that their magnetic state might be lost because of thermal effects, thermally induced magnetic instability, which is commonly known as the superparamagnetic limit. To counter this, the platters are coated with two parallel magnetic layers, separated by a 3-atom layer of the non-magnetic element ruthenium, and the two layers are magnetized in opposite orientation, thus reinforcing EAC. Another technology used to overcome thermal effects to allow greater recording densities is perpendicular recording, first shipped in 2005 and as of 2007 used in certain HDDs. Second point, capacity. The highest capacity HDD shipping commercially in 2021 is 20 TB. The capacity of a hard disk drive, as reported by an operating system to the end user, is smaller than the amount stated by the manufacturer for several reasons: the operating system using some space, use of some space for data redundancy, and space used for file system structures. Also, the difference in capacity reported in SI decimal prefixed units versus binary prefixes can lead to a false impression of missing capacity. Third point, components. A typical HDD has two electric motors, a spindle motor that spins the disks and an actuator motor that positions the read/write head assembly across the spinning disks. The disc motor has an external rotor attached to the discs. The stator windings are fixed in place. Opposite the actuator at the end of the head support arm is the read-write head. Thin printed circuit cables connect the read-write heads to amplifier electronics mounted at the pivot of the actuator. The head support arm is very light, but also stiff. In modern drives, acceleration at the head reaches 550 grams. The actuator is a permanent magnet and moving coil motor that swings the heads to the desired position. A metal plate supports a squat neodymium iron boron, Nib, high flux magnet. Beneath this plate is the moving coil, often referred to as the voice coil by analogy to the coil in loudspeakers, which is attached to the actuator hub, and beneath that is a second nib magnet, mounted on the bottom plate of the motor. Some drives have only one magnet. The voice coil itself is shaped rather like an arrowhead and is made of doubly coated copper magnet wire. The inner layer is insulation, and the outer is thermoplastic, which bonds the coil together after it is wound on a form, making it self-supporting. The portions of the coil along the two sides of the arrowhead, which point to the center of the actuator bearing, then interact with the magnetic field of the fixed magnet. Current flowing radially outward along one side of the arrowhead and radially inward on the other produces the tangential force. If the magnetic field were uniform, each side would generate opposing forces that would cancel each other out. Therefore, the surface of the magnet is half north pole and half south pole, with the radial dividing line in the middle, causing the two sides of the coil to see opposite magnetic fields and produce forces that add instead of canceling. Currents along the top and bottom of the coil produce radial forces that do not rotate the head. The HDD's electronics control the movement of the actuator and the rotation of the disc and perform reads and writes on demand from the disc controller. Feedback of the drive electronics is accomplished by means of special segments of the disc dedicated to servo feedback. These are either complete concentric circles, in the case of dedicated servo technology, or segments interspersed with real data, in the case of embedded servo technology. The servo feedback optimizes the signal-to-noise ratio of the GMR sensors by adjusting the voice coil of the actuated arm. The spinning of the disc also uses a servo motor. Modern disc firmware is capable of scheduling reads and writes efficiently on the platter surfaces and remapping sectors of the media which have failed. In 2004, a higher density recording media was introduced, consisting of coupled soft and hard magnetic layers. So-called exchange spring media magnetic storage technology, also known as exchange coupled composite media, allows good readability due to the